Section 14.5 about directional derivatives and gradients. One quick note, on the homework, they start with gradients, like numbers 1 through 4 is going to be about gradients, but I think it makes a lot more sense to talk about directional derivatives first. So this would be number 5, 6, 7, etc. Okay, when you have a function, z is a function of x and y. And then you go to find the first derivative. Of course, there's two derivatives. One would be the derivative of z with respect to x. You could also take the derivative with respect to y. But what is this actually saying? Well, the top part is saying how much does the z value change? How much does the height change? And then this is saying that you're going in the x direction. So that means that if this is the xy plane, and you're standing in the xy plane, but you're looking up at the function, you have some particular point, and according to this, the only direction you're allowed to go is either to the right or to the left. Nowhere else. So what if you want to be able to go any direction you want? That's the direction for the directional derivatives. Like, for example, let's say that this is a mountain. And you are standing right here at the top. So at one particular point. Now, if you want to get down really fast, then you should go this direction. Or even this direction. That's going to lead you to the fastest path down the mountain. This doesn't really look safe though. If that's a 1,000-foot drop, it's probably not a good idea to go that direction. To be safer, although it would be slower, it would be better to go to the left and go this direction so that you're going nice and just jog right down that hill. Now, how do we actually do it? So first of all, we've got the vector that's going to tell you which direction to go. And then that's usually used, we usually use the letter u for that. So u1, comma, u2. So that would be telling you one of these little red arrows right here, the direction to go. But the important thing is this must be a unit vector. So in other words, it has to have a length of 1 because I want it to tell you which direction to go, but I don't want it to be a vector that is 5 units long because then that is going to actually push you way out here and then you'll just drop down. So the u needs to be a unit vector. That way you're only multiplying by a 1 for its length. It will tell you the direction to go, but it won't affect the size of the derivative. Okay, once you have that unit vector, then here's how you find the derivative. So first of all, we use d for the derivative. U will tell you the direction to go, and then we would have the function. So this is just the notation to say take the directional derivative. Now the way you actually do it is you make a vector out of the derivative with respect to x, comma, the derivative with respect to y. And then take the dot product with the unit vector. So just multiply the first component with the first component plus the second component with the second component. That's the directional derivative. And then for an example or two, so for the first example, let's say that the function is negative x squared minus y squared plus 4. So that would look like a paraboloid that got shifted up, that's upside down because of the negatives, and it got shifted up by 4. And then the point is going to be 1, 0, 3. So at one particular point, then find the derivatives. So find the derivative in the direction u of the function when x is a 1 and y is a 0. Part A, how about if u equals 0, 1? So the length of this vector would be 1, so it's definitely following that rule that this is a unit vector. Now take the derivative with respect to x. So that would just be negative 2x. Take the derivative with respect to y, and that would just be negative 2y. And then we need to plug in the 1 and the 0. So when you plug in 1, 0, that means plug in a 1 for x, so that's going to be negative 2. And for this one, when you plug in the 1, 0, we're plugging in a 0 for y. So negative 2 times 0, that's going to be 0. And then the derivative in the direction u of the function at the point 1, 0 is going to be, so take this vector, negative 2, 0, and dot product with the u vector. In this case, that would be negative 2 times 0 plus 0 times 1. So the derivative equals 0. All right, now let's do the same thing except use a different vector. So part B, suppose that u is equal to 1, 1. Now the problem with this one is the length of this is not equal to 1. The length of this vector would be the square root of 1 squared plus 1 squared. So that's going to be the square root of 2. So we actually need to adjust this vector. So actually use the unit vector. That's going to be 1 over the square root of 2 divided by 1 over the square root of 2 for each one of those. So just take that vector, divide, distribute it to each one. Now this is a unit vector. So the derivative in the direction u of the function at 1, 0 equals, this part's going to be the same. This part is exactly the same. We're only changing this vector right here. So it's going to be negative 2, 0 dot product with 1 over radical 2, 1 over radical 2. So that'll be negative 2 times this one, so negative 2 over radical 2, plus 0 times 1 over radical 2. So in the end, it equals negative 2 over radical 2. Now, take a look at this example. And in this example, the function, so the idea is that there's a lake out here, and then somebody took a map of the lake and they put the x and y axis over the top of the map. And this function, 50 minus 2x minus xy squared, gives the depth of the lake. So if you have some particular point, you've got an x and a y, you can plug them in, and then that's going to tell you the depth at that particular point. So from the surface down to the bottom, how many feet is it? So find the derivative in the direction u at the point 1, 2 if the u is in the direction 3, 4. So in other words, you go to the point 1, 2, and you're at that point 1, 2. Hopefully you're in a boat or maybe out there for a swim, and then you're going to go in the direction of 3, 4. So then go over by 3 and go up by 4. So you're going to be going in this direction. And then find the derivative. And of course, the problem is this is not a unit vector, so we need to use a unit vector. So the length of this thing would be the square root of 3 squared plus 4 squared. That's going to be the square root of 25. So we need to adjust the u. The u must be a unit vector, so divide this by 5. So it's going to be 3/5, 4/5. Okay, now for the partial derivatives. The derivative with respect to x. That'll be 0. This will just be -2. And then this will be 1 times the negative y squared. So -2 and minus y squared. The derivative with respect to y. That would be 0, that would be 0, that would be 2y, and the negative x would still be there. So it's -2xy. And now plug in the 1 and the 2. So the derivative with respect to x at 1, 2, that would be, so there is no x to plug in, but if you plug in that this is a 2, that's going to become 4 negative, and 2 more makes it -6. And then plug in the 1 and the 2. So this will be 1 times 2 is 2 times this, so that's -4. And the derivative in the direction u at the point 1, 2 will be, so create a vector out of this, -6, -4, and then dot product with the unit vector. So when you do this dot product, it's controlling the direction, but because it's a unit vector, it's not making this bigger than it's supposed to be. So this is going to be, let's see, -6 times 3, so -18/4. And then 4 times 4, that'll be -16/5. And how much is that? -18/4 minus 16/5. So it's -7.7. Now what does that mean? What that means is that the depth is decreasing. So if the depth used to be 100 feet, now it's decreasing by 7.7, so now it's 92.3. So it's actually getting shallower. So if the person is swimming this way, it's actually getting shallower. By 7.7 feet for every 1 foot. And I don't know if they're swimming or they're in a boat, so I'll just say 1 foot of movement. So as they move 1 foot, then the lake just got shallower by 7.7 feet. So that's one example. Okay, then on to the second half of today's show, and that is the gradient. So the notation for the gradient is this upside down triangle that's also known as del. And the gradient of f is actually this thing right here. So you take the derivative with respect to x, you take the derivative with respect to y, make a vector out of it, and that's the gradient. So the derivative with respect to x, comma, the derivative with respect to y. There's the gradient. So for the next example, find the gradient of f at 5, 1. So that's it, just find the gradient. And the f function, in this case, is going to be x times tangent inverse of y. So we need the derivative with respect to x. So that means take the derivative right here, that's a 1 times tangent inverse of y. Take the derivative with respect to y. So that means that x just sits there as a constant, take the derivative of tangent inverse. The derivative of tangent inverse is 1 over 1 plus y squared. Now plug in the numbers. So that means substitute in that y is a 1, so that is tangent inverse of 1. And then this one, plug in a 5 for x and a 1 for y. So this is going to be 5 over 2, tangent inverse of 1, that's pi over 4. Let me just double check. Change the mode to radians, take the tangent inverse of 1. Is that pi over 4? Yes, it is. So that means that the gradient is equal to pi over 4, comma, 5 halves. So that way, if we are asked for the directional derivative, we already have most of the work done. All we would need is the unit vector, do the dot product with the unit vector, and then you would have the derivative. Now the gradient itself actually has a very important property. So if you go back to my very first little artwork right here, and you're right here on the top of the mountain. So at this point, what's the fastest way down? Well, the fastest way down would just be slide down this 1,000-foot cliff. That's the fastest way down. Or in other words, when you're at this point, what direction do you go so that the derivative, or your velocity, is going to be maximum? Well, that's what the gradient theorem is about. So the max value of a directional derivative is the gradient. Find the length of the gradient. So the gradient will tell you what direction you should go in order to maximize the derivative. And if you find its length, it'll even tell you what's the fastest that you could go. So back with this picture right here, so the gradient vector would tell you go down this hill, and if you find the length of the gradient, it's even going to tell you how fast you're going to be going. That is pretty amazing. All right, so for the next example. So now I'm going to do one like the homework. So for the next example, f of x comma y is equal to x squared minus xy plus y squared minus y. Find the directional derivative at 1 comma negative 1 all right, so we also need to know u, and that's going to be part of our job. Also find the u. So find the derivative and find the direction you should go so that the derivative is largest. Well, that's what the gradient theorem was all about. So first of all, what's the gradient? So take the derivative with respect to x. This would be 2x. This would be negative 1 times y. Now, take the derivative with respect to y. So this would be negative x, that would be 2y, and that would be negative 1. Okay, so here is the gradient. And we do actually have x's and y's that we could plug in. So if you substitute a 1, that's going to be 2. Substitute a negative 1, the negatives will cancel, so it's going to be 2 plus 1 is 3. And then if you substitute a 1 and a negative 1, then this is going to be negative 1, negative 2, so that's negative 3 so far. With this is negative 4. So find the u so that the derivative is the largest. Well, that means we need to use the gradient, so that is the direction to go. But when it says u, that means unit vector. So I now need to turn this into a unit vector. So 3 squared plus 4 squared, that's going to be 9 plus 16. The square root is 5. So that means that u would be 3 divided by 5, negative 4 divided by 5. So that's the direction to go if you want the derivative to be the largest. But what if it would have said the smallest? Well, then just go in the opposite direction. So for the opposite direction, just use negative of that vector. So that would be negative 3/5, comma 4/5. And then one more part for this one. Oh, hold on, because I didn't quite finish this. I found the u, but I didn't actually find the derivative, so I need to do that. So the derivative so then take this dot product with this. So it's going to be 3 comma negative 4 dot product with 3/5 negative 4/5. So let's see, that would be 9/5, and then negative times negative would be positive 16/5. So that's 25/5, or in other words, 5. And then for this one, because it's just the negative of it, it will be a negative 5. So you could do the same work, but all I did was multiply by a negative, so that means that this would be multiplied by a negative and it would be negative 5. Okay, then I need to do just one more example that is like the homework. So now this is like numbers 1, 2, 3, 4. So you've got a nice simple function, 7y minus 3x. Find the gradient at the point 2, 1. So first of all, for the gradient, take the derivative with respect to x. So that is just going to be negative 3. Take the derivative with respect to y. So that is going to be a 7. And then plug in a 2 and a 1. And it doesn't change it. There's nothing to plug in. Then sketch the gradient and the level curve at the given point. Okay, so what they're talking about here is our function is z equals this. Now, if the point is that x is a 2 and y is a 1, we could plug those in. So x is a 2 and y is a 1. And then that would mean that z is equal to 1 at that particular point. So this is a plane. And when a plane intersects where z equals 1, it's going to create a line. So now take that 1 and plug it back in over here. So at a height of 1, this is the line that it's creating. And then I'm going to solve for y. So I'll add 3x to both sides and divide by 7. So that's the line. So now this is only in the xy plane because it only has x's and y's. This is a line that crosses the y-axis at 1/7. That was really small. 1/7. And then its slope is 3/7. So it's a line that's going about like this. Also, graph the gradient. Well, notice that the gradient is -3, 7. So that would mean go -3, 7, and then go in that direction. But it's supposed to be at the point 2, 1. So if you go -3 and then 7, it's going to be pointing that direction. But take that vector and just move it over to here. So that means that this vector, the gradient vector, is going like this. And it's actually perpendicular. I know that it's perpendicular because this is, if you looked at it as slope, the rise would be 7, the run would be -3. So its slope is -7/3. And this one, its slope is +3/7. So those are negative reciprocals, so it's perpendicular.